The next reaction we're going to talk about is the addition of water to a double bond. This time, I want you to think about water molecule like HOH. Okay? Mechanism is very similar, but basically what we're doing is adding water to our double bond. So a hydrogen is going to go on one of the carbons, and the OH is going to go on one of the other carbons. In this reaction, though, we have to use a catalyst. Last reaction we didn't use a catalyst, but this one we do. And it's a acid catalyst. Okay? Now, there's many different ways to symbolize an acid catalyst. I'm going to show you all of them. All of them are going to be used. You're going to see all these throughout the book. You'll see me use them throughout. You just have to know that these all mean the same thing. Okay? One of the most common acid catalysts that people use is phosphoric acid, and they also might use sulfuric acid. Okay, those are the two most common acids, and they're just the catalyst. We just need the proton from these. The sulfates and the phosphates, they don't do any of the reactivity. Okay, they are the spectator ions. It's the acid itself. So you might see it as just H plus as the catalyst, or you might see it as H3O plus, or you might just see the word acid. Okay, you might just see the word acid above the arrow of a reaction. All right, so let me just show you a very simple generic reaction that kind of gives you the idea of what's happening. And I'll just show you all the players and how it works. So you have your double bond, you're adding water, you have your acid catalyst. I'll put it into H+, but I could have written H3O+, I could have written the word acid, I could have written H3PO4, I could have written H2SO4. There is no exact way, it just depends on what you want to do. And then this reaction requires heat. This little triangle in chemistry is a symbol for heat. Maybe because it looks like a little campfire or something, I don't know. But that's, anytime you see that symbol under the arrow, that just implies heat. So this is, I'm reacting an alkene with water in the presence of an acid catalyst, and the reaction is the same exact thing. You get the same type of product as you do in this reaction as you did in the HX, but this time you have an OH on your carbon rather than an X. Okay? Now, one of the definitions of a catalyst is that it gets regenerated at the end of a reaction. If you use it, you got to reform it at the end of the reaction. Okay? And like I said, H plus is the most common, but you might see it as H3O plus. Okay, so in this case, you'll see that you regenerate an H3O plus, which is the regeneration of your acid catalyst. Okay, so let's talk about this mechanism. Very similar mechanism. You form a carbocation. So Markovnikov's rule is going to play an effect. In this case, since you have equal substitutions on your carbons, we don't have to worry about the Markovnikov rule yet. Okay, because it doesn't matter. It's an equivalent compound. So your double bond is your Lewis base. Your H plus obviously is your Lewis acid. The pi bond grabs the proton. The proton attaches to the carbon. So that means one of the electrons left the carbon to give it a carbocation. Then water is going to add, and remember there's lone pairs, I didn't write them up above, but we know there's lone pairs. This is now my Lewis base. Obviously the carbon positive, the carbocation is my Lewis acid. So these lone pairs, the negative, that partial negative is attracted towards the positive of the carbocation. And that's where the oxygen attaches, but notice you still have 3 hydrogens attached to your oxygen. Okay? So you don't break any hydrogens. Don't magically make things disappear. They're still there. Okay? So your water attaches, but now you have another water molecule come by. Just pluck off that proton, which regenerates our H3O+. So notice this is the regeneration of H3O+, which remember is our catalyst. So that's the regeneration of our catalyst. So that's how you know that's the catalyst. Like I said, the catalyst is regenerated. So now you form your water, and a way of showing how catalyst is spit out of the reaction is by this other arrow showing that the H3O+ is coming off. All right, so that's the mechanism. Very similar. Pi bond grabbing the proton, just like how we saw in the previous example. Your pi bond grabbed the acidic hydrogen on your HCl. You form a carbocation. Your nucleophile in this case is your water molecule. The lone pairs come in to form the bond with carbon. You have an extra proton in this case, so this is Not the same as we saw in the last example, but in this case you've got a proton, and you have to. It gets plucked off by H2O to form H2O plus, which is your catalyst, and ethanol. Okay. So let's try a practice problem. All right. Like I said, sometimes I might give quizzes on these videos. This would be a perfect example of something I would give on that quiz. Hint, hint. All right, so you react it with water, and you have the right water, and you have your acid catalyst, and you're going to heat this. So I'll put the word heat. Okay, so I'm going to put this. Well, I don't have to put it on pause, but why don't you put this on pause? Why don't you write what the product should be based on Markovnikov's rule? This follows now Mark's rule. Okay, just draw the product. All right, I'm assuming you put it on pause. I don't have to pause it. I'm realizing I don't have to hit pause because you have to hit pause. So your product should be, remember, an H goes to one of the carbons and your hydrogen goes to the other. So remember, the hydrogen goes to the least substituted carbon, and the OH is going to go to the most substituted carbon. All right, that's Markovnikov's rule. All right, the H goes to the least substituted. So notice this carbon right here, this carbon has 2 hydrogens. This carbon is attached to 3 carbons. So you have technically you're going to have a tertiary carbon. Here you technically only have a primary carbon once it reacts. So your OH is going to go on the more substituted, which would be the tertiary. Okay? The mechanism, again, remember your pi bond, I'm just going to do it in the skeletal structure, so we can speed it up a little bit. The pi bond grabs the hydrogen, and you're going to form the positive charge at that position. That's a tertiary carbocation. If the hydrogen, so here's your hydrogen, if your hydrogen went on the other carbon, on the tertiary carbon, what kind of carbocation is that? What kind of carbocation is that? That is a primary carbocation. Why is it primary? Because this carbon is only attached to one other carbon. The rest of them are hydrogens. And we know that tertiary is much more stable than a primary, so this is the mechanism it's going through. So that means your water is going to attack at this carbocation on this carbon. So that's where your OH ends up. So just to finish up the mechanism, water comes into here. I'm not going to write that hydrogen in there because we know it's there. I'll give you the plus. And then another water molecule is going to come in and pluck that off. You might be asking, well, in your reaction, you don't have another water molecule. Well, remember, we're an acid. Acid only exists in water. So your solvent, this reaction is done in a sea of water. You have like a quadrillion-fold excess of water compared to your starting material. So there's tons of water around. Okay. The next reaction, so notice this is the way to make a Markovnikov alcohol. There's something called an anti-Markovnikov alcohol. Anti-Marks alcohol. All right, so there's a way to synthesize the opposite. So let's say, so just to remind you, just to show you the difference, all right, if we added the acid and the heat and the water to this, remember the slash just means I'm adding both things to it. Your product, this is just review from last page, just to kind of remind you, your OH is on the more substituted carbon. That's the more substituted. Well, the anti-Markovnikov, let me show you the anti-Markovnikov reaction. That puts the OH on the opposite carbon, on the least substituted. The reagents, there are 2 reagents. This is going to be a little different than what we've seen. You're going to see a 1 and a 2. The 1 and the 2 means it's a 2-reaction process. 2 reactions. Okay? The first reaction is adding the BH3. BH3 is what's called a hydrating, a hydrating agent. And what you're doing is adding a hydrogen onto your molecule. The second reaction is using hydrogen peroxide, all right, in sodium hydroxide. These are the 2 reagents that you use, and what you get in this case is the opposite compound. You get the OH on the least substituted. Okay, so least substituted, more substituted. All right, so you've just learned two different reactions. One reaction, the acid and water with heat, all right, gives you the Markovnikov product. The BH3 with the H2O2. We're not going to go over this mechanism. If you're curious, you can come to my office hours. Gives you the anti-mark. All right, you might be saying, well, why would I want to make one or the other? Well, let's say one of them causes cancer and the other compound cures cancer. Wouldn't it be nice to know how to do a reaction so I can synthesize the curing agent in very large scale? All right, because obviously I don't want to cause cancer, I would like to cure it, okay? So that is why there are two different reactions that do the opposite thing.